Okay, we're continuing with the curve sketching series of videos. In this video, we're going to sketch the function y is equal to the sine cubed of x. All right, step one, the domain. The domain of sine of x is all real numbers, and so just cubing sine of x, the domain is still all real numbers. All right, the range. The range of sine of x is 1 to minus 1. And if you cube anything between 1 and minus 1, then you're still between 1 and minus 1. So the range is the closed interval from minus 1 to 1. Okay, now let's do symmetry first, and just because you'll see why I want to do this first. So let's test for symmetry. Is this an even function? So y of minus x is equal to what? So sine of x that's the main equation. Okay, so now sine of minus x cubed is minus sine cubed of x. Okay, this is not equal to the original function. All right, what about, is this an odd function? So minus y of x is equal to minus sine cubed of x, and this is equal to y of minus x. So we just saw here. So this is an odd function. Okay, now what about periodicity? So if it's if a function has periodic symmetry, then there's a number p such that y of x plus p is equal to y of x. All right, so if we come here and we say x plus, and so the sine function has period 2 pi, so perhaps this also has, this sine of cubed of x also has period 2 pi. Yeah, there you go. So this is periodic with p is equal to 2 pi, which means that y of x plus 2 pi is equal to y of x. Okay, so now I wanted to do that first because you'll see why. You'll see why I want to do this first. So let's check for asymptotes. So what about the y or not asymptotes, intercepts? Okay, what about y intercepts? So set x equal to 0. Sine cubed of 0 is equal to 0. All right. So the origin is an asymptote. Okay, now the x-intercepts set y equal to 0 and solve for x. Okay, so inverse sine, arc sine of 0. Now, if you put this into the calculator, you get 0, but this is one of those that, you know, it's like, it's more, the technical answer to this is like n times pi. It has an n in it. It's certain integer multiples of pi or 2 pi or pi over 2. So, all right, if we think about the unit circle, sine of 0, like at angle, x is the angle. So when x is 0 degrees, then the sine of 0 is 0. sine is on the vertical. Cosine's horizontal, sine's vertical. And so now if you do sine, if you go from 0 and you go to pi, like sine of pi over 2 is 1, sine of pi is also 0. So sine of, it's sine of 0, sine of pi, sine of 2 pi, sine of 3 pi, sine of 4 pi are all 0. So this is, x is equal to n pi, where n is any integer, 0, -1, any positive or negative integer. All right. Now, what we're going to do, though, is we're only going to draw the curve for one period. We're going to go from minus pi to pi. And so in that case, if we're only going from minus pi to pi, then the x-intercepts are x is equal to 0, x is equal to minus pi, x is equal to pi. Okay, and so the graph here will go from -4 to 4, and then from 1.5 to -1.5. That'll give us a good, clear picture of the graph. So pi is 3.14. Each of these ticks is 0.4. So -3.6, -3.2. So right here-ish. Okay. That's pi and minus pi. X-intercepts. And then x is equal to 0 is also an x-intercept and a y-intercept. All right. Next is endpoint behavior. So to analyze the endpoint behavior, you take the limit as x approaches the limits of the domain. So in this case, it's negative infinity and positive infinity of the function. So the limit as x approaches negative infinity of the function is equal to, and this is actually, if you think about it, this is going to be the same thing as the limit as x approaches infinity of the function, and this is going to be does not exist. And why is that? Because if you think about a sine function, the limit as of a sine function as x goes to infinity or negative infinity, it's periodic, and so there is no limit. It's oscillating between -1 and 1. Okay. All right. Next, what we want to do is get the critical points with respect to both the first and the second derivative. So the critical points. First derivative. Okay. So there's the function. Take the derivative with respect to x of the function. Okay. There's no points where, there's no x where this doesn't exist. So all we need to do is find where this equals 0. So we solve for where this is equal to 0. All right, so it's at this x is equal to 2n minus 1 pi over 2, or x is equal to pi n. All right, so x is equal to 2n minus 1 pi over 2. Or x is equal to 2 pi n. All right, now we only want to use x's that are between minus pi and pi because we're sketching one period. All right, so in that case, if we, okay, so when n is equal to 0, what do we have? Minus pi over 2. That's within minus pi to pi. When n is equal to 1, what do we have? Pi over 2. Okay. When n is equal to minus 1, what do we have? Minus 3 pi over 2. That's outside of the range. When n is equal to 2, you've got 3 pi over 2. So, okay, so this is it. Minus pi over 2 and to pi over 2. minus pi over 2 and pi over 2. So here, when n is equal to 0, you have x is equal to 0. When n is equal to 1, you've got x is equal to 2 pi. When n is equal to minus 1, you have x equal to minus 2 pi. So this is it. All right, now what we can do, though, is let's get these points. So E, the original equation with x is equal to 0 is 0. All right, so 0, comma 0. Now, what is the function at minus pi over 2? Minus pi over 2 minus 1. Okay. And now pi over 2, it's 1. Okay. So let's plot these points. So 0, 0. Okay, now minus pi over 2 is about minus 1.6. So 0.4, 0.8, 1.2, 1.6. Okay, and then minus 1. So 0.15, 0.30, 0.45, 0.60, 0.75, 0.90, 1.05, so like around here-ish. Okay, now 1, 2, 3, 4, pi over 2, and then 1, 2, 3, 4, 5, 6, about right there. Okay, so now the critical points with respect to the second derivative. So we've got d squared x, d squared dx squared of the equation. There's nowhere where this doesn't exist, so we just need to solve for where does this equal 0 for what values of x. Okay, so for x is equal to 2n pi minus inverse cosine root 3 over 3, okay? All right, and then x is equal to 2 pi n plus inverse cosine root 3 over 3. And actually what I'll do is so plus or minus. Okay, then we've got x is equal to, well, let me bring this further down. So x is equal to 2n pi minus inverse sine root 3 over 3 minus pi over 2. Okay. And this is also going to be like plus or minus inverse sine root 3 over 3. And then this will be plus or minus pi over 2. Because you can see the next equation is the same equation, but with it's the same exact equation, but with pluses instead of minuses. All right, and then x is equal to pi n, not 2 pi n, pi n. So x is equal to pi n. All right, so now for what values of n do we get an x that's within minus pi to pi? So, all right, let's get this. So this here, we'll just call this n. Store that as x1. There we go. Okay. All right. So x1 with n is equal to 0 is minus 0.955. Minus 0.96. Okay, that's within minus pi to pi. All right, x1 with n is equal to 1 is, that's greater than pi, so no. x1 with n is equal to minus 1. That's less than minus pi, so okay, that's it. All right. Now let's take this one here. I mean, we know that from since this is an odd function, we know that x is equal to plus 0.96 is going to be a point, but let's just do it this way. Let's just go equation by equation here, right? Because we know that for any given point, like minus pi over 2 minus 1, well, if we multiply this by each component by minus 1, we're going to be on the graph because it's an odd function. That's why this point shows up. So we know that I know x is equal to 0.96 is going to be another point, positive 0.96, because it's an odd function. But still, let's go through each of these individually. All right, so this we'll call x2. All right, so x2, yeah, okay, x2 with n is equal to 0 is that there's positive 0.96. And let's just check each of these. Nope. Or minus 1. Nope. Okay. All right. So now let's come to this one here. All right. Okay. We'll store this as x3. Okay, so now we go x3. No, wait, we say, yeah, that was it. x3 with n is equal to 0. All right, now that is, okay, that's within minus pi to pi, so minus 2.19. Okay, and then x or n is equal to 1. 4.09, no. No, okay. So then next we want to do, so it's this same equation, but we put pluses here. And we'll label this x4. All right, now x4 with n is equal to 0. Yeah, and we know that it was going to be positive 2.19 for sure. Okay, now what about n is equal to 1? Nope. N is equal to minus 1. No. Okay. Now here in pi, n is equal to 0. X is equal to 0. N is equal to 1. You have pi, and then you also have minus pi. Okay. So now let's get these as points. So, okay. What we'll do is, so the original equation, the original function with x is equal to minus 0.96. So minus 0.55. All right, and then we multiply each component by minus 1. Okay, now 2.19 0.54, so 2.19.54, and then multiply each component by minus 1. It's an odd function. Okay, now pi zero. Okay, so pi 0 minus pi 0 and then 0, 0. Okay, that's all. These are all the points, critical points with respect to the second derivative. These are the critical points with respect to the first derivative. All right, so let's plot these points. So minus 0.96 minus 0.55, 0.4, 0.8, 1.2, so 1.0 about right here, and then 0.15, 0.30, 0.45, 0.60, so this is about 0.55. Okay, so now we do, it's an odd function, so we come to about here, and then 1, 2, 3, about right there. Okay, that's these 2 points. Now 2.19.54. So let's go in the negative direction first. So minus 0.4, 0.8, 1.2, 1.6, 2.0, 2.4. So this is minus 2.2-ish. Now minus 0.54, so we come even with this point at the bottom. Okay, 3, 4, 5, 5.5. And then come even with this point. Okay, and then these are x intercepts. All right, there we go. Now, as far as asymptotes, there's no horizontal asymptotes because we took these limits going to infinity. And as far as vertical asymptotes, if we didn't know the function at all, we know that the sine doesn't have any vertical asymptotes. The sine function, if you're just cubing the sine function, there's not going to be any vertical asymptotes. But in general, what you would do is, if you're just trying to analyze a function kind of blindly, what you would do is you would take all of these critical points with respect to the first and second derivative and take the limit as x approaches each of them from the left and the right. If any of those limits go to infinity, it's a vertical asymptote. We're not going to do that because we know there's no vertical asymptotes here, but just pointing that out. All right, next let's get the intervals where the function is increasing and decreasing, as well as the intervals of concavity. So to do this, we need to take these critical points. Okay, so the function the first derivative of the function can change from positive to negative at a critical point only. Critical point with respect to the first derivative. So, all right, 0, and then say this is pi. Let's just put the full period, or no, minus pi, and then pi. All right, so minus pi over 2 pi over 2. Okay, so we're only changing at these points here. Okay, we don't change at pi or minus pi. So, all right, so now what we do is we take the first derivative, all right, and now evaluate this with x is equal to, let's go within these intervals. So minus 0.25 pi. Okay, so this is positive, so increasing. Okay, and now let's do 0.25 pi. So now it's still increasing. And then when we cross over to, let's say, 0.75 pi, now it's decreasing. And then I'm assuming it would be decreasing here as well. So this would be minus 0.75, yeah, decreasing. Okay. Yeah, there we go. Now, here, for the intervals of concavity, we go from minus pi to pi. Okay, we have 0 as a crossover point. We've got minus 2.19. Let's see here. Okay, so pi over 2 is about right there. That's about 1.6. So 0.8 is about here. So this is about 0.96. 0.8 is about here. So minus 0.96, 0.96. Okay, and then, 2.19 is about in here. Okay. So there's all of the, I don't know if that's evenly spaced. It's kind of this, I don't know how it's, let me change this. Get this to where it looks more spaced out evenly. So, yeah. Yeah, there we go. Okay. Oh, and then pi and minus pi are also 1, 2, 3, 4, 5, 6, 7. There's 4 crossover points. So let's take the second derivative. All right. With x is equal to, let's do minus 2.9. All right, so concave down here. Now let's do positive 2.9. Concave up here. All right. Now let's do minus 1.5. Concave up. All right, positive 1.5. Concave down. Okay. Minus 0.5, so now concave down. Now positive 0.5. Concave up. Okay. So, next, what are the local maxes and mins and the inflection points? Well, this function is continuous everywhere, so when local maxes and mins, we just check at what critical points does the first derivative change from positive to negative or negative to positive. So here it goes from decreasing to increasing. So this is a, decreasing to increasing. This is a local min. Increasing to increasing, that doesn't change. Increasing to decreasing, this is a local max. Okay, inflection points, the function has to be continuous. It's continuous everywhere. So when it's continuous, you just see at what critical points with respect to the second derivative does the concavity change sign. So it changes. So here it's an inflection point. Here it's an inflection point. and even at pi and minus pi. Okay, so now let's sketch the curve. So at each x-intercept, the slope's going to be 0. So we need to make sure we illustrate that. So we know this is going to be concave down, right? We're going to have a 0 slope at each of these x-intercepts, okay? And then we'll also have a 0 slope. This is a local min. This is a local min, all right? And so, okay. So we're starting here from minus pi to 2.19, we're concave down. And then we're going to switch to concave up there. So let me try and get this right. Okay, then we switch to concave up. All right. You see, we've got that 0 slope here. We want to make sure we do that 0 slope at the x-intercepts. Okay, you see how we have that 0 slope there? And so there, that should be it. So let's make sure everything makes sense. We know we have the x-intercepts correct. We've got the, all right, now starting from, and we have 0 slopes at what points? So yeah, these aren't going to be local maxes or mins because we get here and you can, why isn't these 2 points at the end local maxes or mins? It's the same reason this isn't a local max or min. At the x-intercepts, you don't have a local max or min. Okay, it doesn't change from, it goes increasing, increasing, or decreasing, decreasing. All right, but the slope is still 0, but it's not a local max or min. Here, you've got a local min. Here, you got local max. And that's what we see. Pi over 2, local max, minus pi over 2, local min. All right, now we start off, we're decreasing concave down. In fact, we're decreasing all the way to pi over 2, negative pi over 2, and that's what we see. But we start off concave down to minus 2.19, then we stay concave up all the way past minus pi over 2 to here. It's minus 0.96. So this is an inflection point here. It's an inflection point here, and it's an inflection point at the x-axis. These three are 1, 2, 3, 4 inflection points in this interval here. All right. So we're decreasing all the way to here. We're concave down, then concave up. Concave up, but we've changed to increasing, right, in the middle of this. And then we've stayed increasing and switched to concave down. Then switched back to concave up, stayed increasing, increasing, increasing. We're switching concavity, and then we switch to decreasing. So this is it. This is the curve. And remember, it's periodic, so if you want go from, you could extend the x-axis and just redraw the same curve. The period is 2 pi. This is 2 minus pi to pi is 2 pi. This just repeats. This same thing repeats.